technical difficulties, so I had to make another video to finish off points 2 and 3 of the real gas theory. So, whoops. So, if you have an ideal gas, you said there are no attractive forces. Between the gas particles. So these things are moving about randomly and hitting the sides of the wall randomly, okay? But with a real gas, the gases do have attractive forces. And some gases have stronger attractive forces than others. So I'm going to just take water, because water is one of the most attractive gases. There's a partial negative on the oxygen and a partial positive on the hydrogen. And the partial negative on the oxygen is attracted to the partial positive on the hydrogens. So what you have is there's a different size font there. So you have an attraction between the partial negative of the oxygen and the partial positive of the hydrogen. So you've got that intermolecular force, and by the way, that's called a dipole-dipole force, or a hydrogen bonding, more correctly. So since there's an attraction between the gases, they're not going to hit the wall with as much force because there's an attraction pulling them together. So they can't hit the walls of the container with as much force. Therefore, the pressure that you would predict is actually less than the real pressure. So you have to adjust the pressure by A, which is the attractive force. So how attractive is the gas? N is the number of gas particles. V is the volume. And because the attraction is mutual, as you saw, I wrote a double-headed red arrow. I didn't just say this one is attracted to that one. They are attracted to each other. The attraction is mutual. And so the force of the attraction gets squared. Okay? So the pressure then is, the pressure must be adjusted by the attraction times N over V squared. Okay? So when we adjust our equation, the ideal gas equation is PV equals nRT, but the real gas equation becomes okay? That is the real gas equation. 1 second here. I have to do a little math. And that will give you a chance to copy down that equation. The reason why it's added and not subtracted is, think of it as, let's just start with V minus NB gets substituted in for that. Okay? So this volume here is not quite accurate, so this thing gets substituted in for that. Likewise, this pressure here is not correct. It's too big. So I'm going to call this P ideal. This is P real. So P ideal minus A over NV squared would actually equal the real pressure, right? Because what was I saying up here? I was saying that these particles don't hit the wall with as much force. So the pressure is actually smaller than what is predicted, because the molecules attract each other so they don't hit the container with so much force. So P ideal minus that gives you the real pressure. So then if I were to do a little bit of math here, P ideal is equal to P real plus A over V squared. Okay, so that's why it's adding, not subtracting. They don't use the subscripts ideal and real, but that kind of helps explain why the real gas, you're putting a plus sign there. Okay, so I'm just going to rewrite the equations. So here's the ideal gas equation, PV equals nRT. This is the real gas equation, P plus A over NV squared. So I'm just going to then square that. Oh, I forgot to say YN over V. So the attraction is going to depend on how many gas particles. So if you have more gas particles in your container, you're going to have more attraction. So that's why the N is a part of the equation. The second reason why is if you have a small container, your gas particles are more likely to bump into each other than if you have a big container. So if there's a big container, there's less likely to be attraction. So that's why the N V are in the equation. And like I said, because the attraction is mutual, you have to square it. And so then they both end up getting squared. And then we already talked about this part equals nRT. Okay, so you have these two equations. So then why do we use the ideal gas equation when it's not right? The real gas equation actually is real. It predicts, it is based on how gases really behave. So the way I kind of look at this is, ideal gases and real gases are kind of like our ideal partner or spouse. So, we all have our ideal partner, 6 feet tall, blue eyes, loves puppies, likes to go for long walks. The fact of the matter is, our ideal does not exist. Okay, your ideal partner doesn't exist. I'm sorry to burst your bubble, but they don't exist. In reality, we have to be with someone who's real. Okay, we don't. So the ideal partner doesn't exist. Similarly, an ideal gas does not exist. Okay, so then why do we do all these math problems using the ideal gas equation when it doesn't exist? The reason why is because the ideal gas equation gives us the right answer 99.9% of the time. So why use this really complicated equation here if the ideal gas equation gives you the correct answer 99% of the time? Okay? So when do you have to use the ideal gas equation? You must use it really kind of depends on each gas, but usually you use the ideal gas equation, real gas equation when pressures are really high. Okay, so let's just give you an example here. So here's my container. Here are my gas particles. Sorry. 2, 4, 6, 7, 8, 9, 10. Well, what if I compress that volume down into a very small area? Now, there's much more likelihood that there's going to be attraction between those gas particles because they're so close to one another. And therefore, the pressure is going to be different. Also, the size of the volume is small now compared to the size of the gas molecules. So, when we look at the ideal gas equation, if we were to graph it as ideal, they go right through the origin. But with a real gas, what happens is you get to a point where you can no longer compress that gas anymore. What happens is, as you compress the gas, it'll eventually turn into a liquid, and if you really compress it, it'll turn into a solid. So what happens is the line goes straight. At the very end, it tails off, and there's a certain point you can't compress your solid anymore because it turns from liquid into solid. So at very high pressures, you must use the real gas equation, okay? So when it comes to the AP test, they're not going to ask you to use the ideal gas equation, but they're going to ask you questions like this. Predict which gas is least ideal. Okay, so first let's tackle the V minus NB portion. So suppose they gave us these gases. Let's keep it simple to begin with. Let's do, well, actually, no, we need to look at the attractive force first, sorry. So let's look at these gases. Neon, carbon dioxide, hydrogen, and then water, okay? So we look at these gases to begin with. So the first thing you want to look at is really like who's got the most attractive force, okay? That's sort of a bigger factor at play. So first thing you want to ask yourself, is your gas polar or non-polar, okay? Because if the gas is polar, there are going to be there are going to be dipole-dipole forces present. If it's nonpolar, the intermolecular forces are going to be van der Waals, also known as London dispersion force. And if you don't remember what these are basically temporary dipoles that last for milliseconds, okay? So, of the gases up here, neon, carbon dioxide, water, and H2O, neon is just a big solid ball, okay? Carbon dioxide is a symmetrical molecule and nonpolar. Because this is just a solid ball, the neon must be nonpolar. Hydrogen is also symmetrical, so it's nonpolar. The only one that's asymmetrical is water. There's 2 lone pairs of electrons there, 2 lone pairs of, so it's got a partial negative, partial positive. Because this thing is polar, it's going to have dipole-dipole forces. So this is going to have the biggest A value. Okay? The most attractive A value. So you always look at to see who's polar first. Now, what about the rest of them? So we're going to rank water as number 1. The rest of these are nonpolar, so the rest of these are all dealing with van der Waals forces. So then you're going to look at basically the size or the mass of the, I should say, you're going to look at the mass of the molecule. So hydrogen is 2, okay, a weight of 2. Carbon dioxide is a weight of 44, and neon's a weight of 20. So what I would expect, and if I was predicting, I would expect that carbon dioxide would have the second greatest forces because it's a bigger molecule, it's got a greater mass, so its van der Waals forces will be bigger. Then would come neon, and then last place, hydrogen, okay? So that's what I'd look at first if someone was asking me which was the least ideal, is I would look at the attractive force first, okay? And again, you look at whether it's polar or nonpolar. If they asked you to base the answer only on size, then they're basically asking you to look at the B factor. So, which of the following gases, that's kind of explained in the second part. So like if we had C2H6, C4H, C6H14. So these are all nonpolar molecules. So who's the biggest? So that one's going to deviate the most from the ideal gas theory. All right? That's it for theory in Chapter 5, gas laws. Now it's just a matter of doing problems.